There's no sound here, but maybe we don't need it. Oh, it's my fault. Okay. So here, evidence for thermite. Then we have there's detected molten iron in the rubble under World Trade Center in abundance. There's issues reports on the molten iron in pools and in streams. NASA flew over the site with the heat-sensitive infrared camera, and they made a thermal map of the area. And according to this is not a geographical map, it's a thermal map. The temperature here on September 16th was 750 degrees. Over here it was 730 degrees. And this was after September the 14th, where there have been heavy rain showers. And still the temperature is far beyond what you would expect from some ordinary office fires. So something was going on also in the rubble, which is unexplainable from conventional seas. Can
you hold that? Just point it for me.
It's not satellite, it was a plane flying.
Yeah, just a minute.
So this molten iron, which is a product of the thermite reaction, has been discovered under the rubble. And actually something was going on in the rubble. It took them 3 months actually to put out the fire, and they did what they really pulled millions of gallons of water from the Hudson River onto it. And they used an artificial fire suppressant called pyrocool to get it out. They couldn't get it out, it took them 3 months. This is a story on its own. Another thing, discovery in the dust, which is iron spheres, tiny balls of iron. And this was revealed in 2 reports from the U.S. Geological Survey and the R.J. Lee Group as early as December 2003. Now, why is this important? I'll tell you why. And by telling a story about some dust sample from Jeanette McKinley, who lived on the corner of Cedar Street and Liberty Street, which is here, I think. And she could look at the plaza, and she ran when the South Tower fell with a wet towel around her face, very wisely so, because the dust was quite toxic. She got away, and this is what her apartment looked like when she came back. Now she was contacted by a physicist called Stephen E. Jones, who I know has been here in Sydney, also on the basis of these report on these iron spheres. He wanted to have a look on his own. And he got a sample from Jeanette McKinley, and this is how it looked like under an electron microscope here to the left. Some of these dust samples dust particles are ordinary, but here you see these round spheres, and here is a close-up of it. Now, how can an iron particle become perfectly round? There's only one basis, thermal history, for this observation, and this is that the iron has been molten and has been upflying. This is a property of liquids in drops. If you have a close-up of the fog or the skim milk, where you can see the fat floating around. When a drop is flying, it acquires a completely spherical shape. This is due to something called surface tension. And so this is an indication of this iron has been molten and it has been flying. And what to do, obviously, is to do experiments. This is what we love. And Stephen E. Jones did just that. He fired a thermite in the corner of the laboratory. The white cloud up here is iron oxide. This is the other product of the thermite reaction. It's sputtering around like the thermite on the French car. And afterward, you collect the dust. This is commercial thermite. You can buy this on the web. Play with it. Don't. So this is the dust from the commercial thermite collected, and this is the dust from the World Trade Center. and it contains exactly the same ion spheres. And now I have to bother you with a little bit of technology, because what we are doing is something called energy dispersive spectroscopy. In short, we heat such a particle with an electron beam, and this can be done with an accuracy of down to 100 nanometers, which is 1/10,000th of a millimeter. We can hit one spot here with an electric beam, and there comes a signal back in form of X-rays, and these you can analyze. And this is such an analysis of the X-ray response from this method. And from the different peaks at the different frequencies, you get information exactly which elements are on the spot you hit with the electron beam. And the lesson to learn here is you have the same ingredients in the ionospheres from the commercial thermite and from your WTC dust. This is Fe means iron, Ca means calcium, Si means silicon, Al is aluminum. There's another iron line here. You see the same elements here from the commercial thermite. With one single exception, if you may notice, there's a little S here, this is for sulfur, and the calcium peak here is a little bigger than over here. This is a contamination of calcium sulfate, which is the chemical name for gypsum, plaster of Paris, which is used for wallboards. So this is because the whole center of the towers, I don't know about 7, but the towers, the center, the core, was embedded in wallboard, which is a brilliant isolator for fires, gypsum. And this is contamination from there into there. Okay? Now, Jones asked himself also the question, when you use an explosive or an incendiary, there's always something left. The process does never run to completion. So maybe there would be a chance to discover unreacted thermite in the dust. And yes, the answer was yes. Among others from the sample from genetic material. Here you see such a remain from a thermite reaction. But this is not the same kind of thermite which was used on the French part. This is, we call it nanothermite, because it has been prepared by nanotechnology. It's a basically fundamentally different way of producing materials than usual. If you have to make a finely divided powder, what you usually do is you take something bigger and grind it. Okay? So you make something bigger, smaller. In nanotechnology, you start from, it's a bottom-up approach. You start from the atom, so you build the material from the atom upwards. This has two very important consequences. One thing is that everything gets smaller. We are operating on a scale of length here. 1 nanometer is 1/millionth of a millimeter. It's very small. And so this is the scale you're operating. It's a little bigger than atomics and molecules, but it is beyond molecules. And the other thing is that in this procedure, you have the option of adding other substances to the material. So, and because everything gets smaller, it reacts faster and more efficiently. And because you have the option of putting in other stuff, you can use the energy of the thermite for actually converting it into an explosive.